Hi guys, welcome back to my channel. In this tutorial, I'll be taking you through review exercises on applications of differentiability. In our previous lesson, we did a part 1 of applications of differentiability. So we continue with the part 2 in this section. So I have a series of questions here for us to go through. So kindly get seated, have your calculator and your materials with you as I take you through all this problem for exams preparation. So let's take the first question and see how to solve it. The first problem says, does the function f of x, which is equal to, so let me write it here, f of x equal to x squared minus 4x plus 1 within the interval 0 to 4 satisfy the Rolle's theorem? And he said, if yes, find c. If yes, find c. So we are just to test if this function here satisfies the Rolle's theorem. Then if yes, we have to find c. Now, in our previous tutorials, we delved into Rolle's theorem, right? And we found out that when you say Rolle's theorem, f of a should be equal to f of b, right? That is, the function should have the same functional value at each endpoint, okay? So if I find f of 0 in this manner, it should be equal to f of 4. And when this condition is satisfied, we can go ahead towards find our c, which says that f prime of c should give us 0, right? So now let's see, let's find f of a and f of b and compare. For f of a, that is f of 0, I'm going to have my f of 0 to be equal to 0 squared minus 4 multiplying 0 plus 1, right? So I'm simply going to have 1. Let's check f of b. B is 4, right? I'm going to have f of 4 to give me 4 squared minus 4 multiplying 4 plus 1, right? And remember, 4 squared is 16. Then here it's 4 times 4. So 16 minus 16, that's going to give me 0 plus 1. I also have 1. So since our f of a is equal to our f of b, obviously you say that it satisfies the Rolle's theorem, right? Because all polynomial functions are continuous. Rolle's theorem works on continuous function. And remember, there is no input that's going to make a polynomial function undefined. So therefore, the polynomial function automatically is a continuous function. And now we found out that f of a is equal to f of b. We can say that indeed it satisfies the Rolle's theorem. So now let's go ahead and find our c as the question asked. So you know that Rolle's theorem says that f prime of c should give us 0. Then we can find the value of c. So meaning that we have to find f prime of x first. So to find f prime of x, we're simply going to have 2x minus 4, right? So once we have 2x minus 4, we find f prime of c. So whenever I see x, you put what? C. So 2c minus 4. And 2c minus 4 should give us 0. Therefore, 2c will be equal to 4. And my c is simply going to give me what? 2. And that is all. That answers the first problem. Now let's go to the second problem, which is also Rolle's theorem. So it says, does the function f of x, which is a quotient, so my f of x is simply equal to x squared minus x minus 6 over the expression x minus 1. Does it satisfy Rolle's theorem over the interval -2, 4? If yes, find c. If yes, find c. So as we did in our previous problem, we are simply going to test for f of a and f of b, f of a and f of b. But first of all, let's see, is our function actually continuous over this interval? Remember that our function, since it's a quotient, at the point s equals 1, the function will be undefined and there will be discontinuity. But do we have 1 as part of our interval? Probably yes, right? Probably yes. So since we found a discontinuity, let's hold on with our discontinuity. Then let's find f of a, right? So what is f of a? That is f of -2. F of -2. And what is f of -2? Wherever I see my x, I'm going to put -2 there. So I'm going to have -2 all squared minus -2 minus 6 all over -2 minus 1. Okay, this gives me 4. 4 plus 2 giving me 6. 6 minus 6, that is 0. So obviously this is 0. So let me find f of 4. That is my f of b, which is going to give me 4 squared minus 4 minus 6 all over 4 minus 1. 4 squared is 16. 16 minus 4 is 12, right? is 12. Then 12 minus 6 is 6 all over 3, giving me 2. Now you can clearly see that my f of a is not equal to my f of b, and also my function is discontinuous at the point s equals 1. Therefore it doesn't satisfy the Rolle's theorem, right? It doesn't satisfy the Rolle's theorem. Okay, the Rolle's theorem. So right now we've seen the first and the second problem, right? Let's move straight to the third problem. Let's move straight to the third problem here. Okay, so let's see. Let's see. So let's see for the third problem. That is for mean value theorem. Mean value theorem. Mean value theorem. So let's see how we're gonna handle that one through here. Okay. So let's see. So there's a function f of x which is equal to s cubed minus x over the interval 0, 2. Does it satisfy the mean value theorem? If yes, find c. Now we dealt into the Rolle's theorem in our previous question. Is now mean value theorem. What does it say? It says that generally f prime of c will give us f of b minus f of a all over b minus a. Okay, all over b minus a. But in this situation, b will not be equal to what? A. Because once b is the same as a, you have undefined situation. Okay, so b should not be equal to a. That is our interval, and probably there is no way you get an interval where b will be equal to a, right? So you can see that Rolle's theorem is a special case of the mean value theorem. Okay, Rolle's theorem is a very special case of the mean value theorem. So now let's see. For this problem, the function is f of x is equal to s cubed minus x, and the interval is 0, 2. Okay, so we straight away find our f of a and our f of b, right? So our f of 0 will give me 0 cubed minus 0, and that is 0. My f of 2 is simply equal to 2 cubed minus what? 2, and that is 8 minus 2, which is 6. Okay, so at this point I have 6 minus 0 over b minus a, that is 2 minus 0, right? 2 minus 0, and it should be equal to f prime of c. F prime of what? C, right? It should be equal to f prime of c. So let's see how we're going to do that here. See how we're going to do that one here. So we're gonna have here will give me 3. Okay, so 3 will be equal to f prime of c. Now the reason why we have got, or the reason why we can go ahead and say that it satisfies the mean value theorem is, you know, if it doesn't satisfy, then you have an undefined term somewhere, right? But you realize that our function really satisfied everything, but we just move straight finding our c. 3 will be equal to, now f prime of c will be what? When I differentiate this, 3s squared. So let me make it 3c squared straight away minus what? 1. Okay, so at this point what do I get? I'm going to get I'll send this there, so I'll have something like 3c squared minus 4 equal to 0. Minus 4 be equal to 0. Or you can say that 3c squared 3c squared will be equal to 4. Therefore, c will be equal to plus or minus square root of 4 out of 3. Plus or minus square root of 4 out of 3. So now let's see. For the fourth question, that is about linearization. Okay, how to linearize a function. And to linearize a function, you only need so let's see something here. To linearize this function, you have to linearize it at a certain point. But looking at the question given, they only give us the functions, right? They only give us the function. So we can't linearize it generally. Because for linearization, L of x generally should be equal to f of a, but here is g of x, right? So g of let me make it g of a plus, right, g prime of x, g prime of a multiplying x minus a. So this is the concept of linearization. You first find the functional value at that point you really want to linearize, okay, then plus the derivative at that point multiplying x minus what, the change from the, you subtract that point from x, gives us the linearized what form. And since you don't have any points here, then our question becomes incomplete because you can't just linearize this function generally, right? So let's move straight to the fifth question here. So it says that the position at time t of a moving particle is given by s of t, okay? Find the time at which its instantaneous velocity s prime of t is equal to its average velocity in the interval t, right? So let's see how we go by this problem here. Okay, so let's see here. So the position. So now we have three different functions here. So we take them one after the other. So I have s of t is equal to s squared plus 2x minus 1. Then t is equal to the interval 0 comma what 1, right? So we are saying that the position at any time t, right, is given or is described as a function of what, t, s of t. That's the position. You know that change in position per time gives what we call the velocity, right? That is why we say s prime. When you differentiate our position here, we are getting what, our velocity. But they are saying that we should find the time at which our derivative or our change in what, our position, will be equal to the average velocity in the interval. Now, once you hear this average velocity, what should come in mind is mean value theorem. Mean value theorem, right? So the word mean here, is what, average, right? So obviously you can say average value theorem. So it's just an application of the differentiability, specifically mean value theorem, which has been framed in this motion problem. Okay. So simply we find out s prime of t, then we equate it to what? S of what? Minus s of what? A. All over b minus a. Where our b and a is the time interval given. Okay. So straight away from this problem, we simply have our s prime of t to be what? 2x plus 2, right? Should be equal to my s of b. What's my s of b? And my b is 1, right? So when I put 1 here, I'll get 1 squared plus 2 multiplying 1, that is 3. 3 minus 1, that will give me 2. Okay. So I'll have 2 minus s of a. Wherever I see x, I'll put 0 there because my a is 0, right? So putting 0, I'll have here to be 0, here to be 0, I'll have negative 1. So I'll put my negative 1 here. All over my b, which is 1 minus 0, okay? So 2x plus 2 will be equal to 3 on 1, and that is 3. So obviously, I'm going to have 2x plus 2 to be equal to 3. Therefore, 2x will be equal to what? 1. X should be half, right? So now, for the first part, we are saying that at time t equals half second or 0.5 second, our our instantaneous velocity will be equal to the average velocity. That is for this part. Now let's see the second one, which says s of t is equal to t plus 1 out of t, where the time interval is given as half comma 2, right? So this one, we follow the same approach. We find our s of 2. What's s of 2? S of 2 give me 2 plus 1 over 2, that is 2.5. Then s of half. So s of half will give me half plus what? 1 over half is what? 2, right? So it's half plus 2, right? And that is also giving me 2.5. So from this side, we can see that this one instead satisfy the Rolle's theorem, right? As I said, Rolle's theorem is a special case of the mean value theorem when our f of a is equal to our f of b, or the functional value at the endpoint are the same. Okay, for that reason, we simply see that we are going to have our s prime of t going to give us 0 because s of 2, s of half are the same. I'll obviously get 0. Then what is s prime of t? I'll differentiate and I'll have, when I differentiate t, I'm going to get 1. So s prime of t will give me 1. Then this side will give me, this is the same as t to the power negative 1. And that will be negative t to the power negative 2, right? So minus, right? So we're going to have negative t to the power negative 2. So minus 1 over t squared. 1 over t. So that's the derivative. And you are saying that it should be equal to 0. Okay. So the next thing is I'll multiply through by my t squared and I'll have t squared minus 1 is equal to 0. So here difference of t squared, I'll have t to be equal to plus or minus 1. Plus or minus 1. That gives us our time. But time cannot be negative, right? So you have to choose a positive magnitude. That is what? 1 second. Right? 1 second. And indeed, 1 second falls within this interval. Finally, let's take the last section as the last rate given here. How are we going to solve that here? So I'm gonna have yeah. So I'm going to have c s of t is equal to square root of t minus 1, where t is equal to 1 comma 3, right? So here, as usual, we find our s of 3, and that is going to give me square root of 3 minus 1, that is square root of 2. I'll find my s of 1, and that is going to give me 0 because 1 minus 1 is 0. Square root of 0 is 0. Then, since they are not the same, yes, we move ahead to the mean value theorem. Then, I take my derivative, s prime of t. So this is the same as what? T plus t minus 1 to the power half. This composite function. So obviously I'm going to have 1 out of 2 multiplying t minus 1 all to the power negative half. Is that not it? And when you multiply the inner function to give us 1, so there is no need to go by that. So with my simplification, I'm going to have 1 over the expression 2 square root of t minus 1. And this should be equal to my root 2 minus, s of 1 give me 0 minus 0 all over 3 minus 1. This is mean value theorem. Mean value theorem. That is how. So let's see. So here I'm going to get 1 over 2 root t minus 1 to be equal to square root of 2 over 2. So what do I do? And I want to find t, the time. So I'll simply cross multiply. I'm going to have 2 to be equal to 2 come here. I'm crossing it this way. These two multiply this. But for this side, I'm going to have 2 root t minus 1 multiplying root 2. So how do we do this? Whenever roots and roots are multiplying, we instead multiply the what? The radical radicand. Okay, radicand. What's within the radical? So 2 will be equal to 2 multiplying the expression. So here I'll get 2t minus 2 all under the square root sign. So that these two can cancel these two. I'll have 1 to be equal to the square root of 2t minus 2, right? When I square both sides, I get 1 is still equal to 2t minus 2. And I'll send it there. 2t will be equal to 3. Then obviously my time is equal to be 3 over what? 2, which is 1.5 seconds. And you can clearly see that the interval starts from 1 to 3. So surely we can spot 1.5 within this interval. So this is the end of our applications of differentiability. So see you in the next section as I take you through the integration